In this video, we're going to look at Chapter 18, Section C on the multiples of 30 and 45. Let's consider the angle theta, 45 degrees. And we also know that this is equal to pi over 2 radians. Now let's look at a unit circle with a point that corresponds to an angle of 45 degrees. We can draw the lines OP, OB, and BP to form a right triangle. And we know that this angle is 45, and because it's a right triangle, the other angle also has to be 45. By inspection, we see that this is an isosceles triangle, and that both lengths of the triangle are equal, and they're both, we'll call length A. By Pythagorean's theorem, we see that a squared plus a squared is equal to 1. And with a little simplification, we get 2a squared equals 1, or a squared equals 1/2, or a is equal to 1 over the square root of 2. And remember, we like to rationalize our denominators, so this is really square root 2 over 2. And that can be approximated to a decimal using our calculator, and we're going to get about 0.707. Because this length of the triangle, because this length of the triangle is the same as this length of the triangle, the coordinates, the x and y coordinates for the point P are the same. Therefore, the coordinates for the point that corresponds to a 45-degree angle are square root 2 over 2 and square root 2 over 2. And notice that I'm only using the positives here because cosine and sine are both positive in the first quadrant, and we learned that in the last section. We can also write the coordinates of this point, or approximate the coordinates of this point as 0.707, 0.707. We can now quickly find all of the coordinates for the angles that are multiples of 45 degrees. Let's take a look at another blank unit circle. Let's fill in the multiples of 45 degrees. They are 45 degrees, 135, 225, and 315. Remember that we know the coordinates of the point at 45. They are square root 2 over 2. We know that the coordinates, or the y-coordinate of 135 is going to be the same as the y-coordinate of 45. And that's a positive square root 2 over 2, because sine is positive in the second quadrant. But we're going to have a negative square root 2 over 2 x-coordinate for an angle of 135. Likewise, we're going to have a negative x-coordinate for the angle of 225 because cosine is negative in the third quadrant. Sine is also negative in the third quadrant. So the y-coordinate of this point is going to be negative square root 2 over 2. And in the fourth quadrant, cosine is positive because the x-coordinate is positive. So I'm going to have an x-coordinate of square root 2 over 2 and a y-coordinate of negative square root 2 over 2 because sine and the y-coordinate are negative in the fourth quadrant. So if you can remember, or remember how to find or calculate the x and y coordinates of the point at an angle of 45, you can quickly find the x and y coordinates of the points for the angles of multiples of 45, 135 degrees, 225 degrees, and 315 degrees. We can do a very similar process for the multiples of 30 degrees. Let's now consider theta to be equal to 30, which we know is, let's now consider the angle 60 degrees, which we know is equal to pi over 6 radians. And let's take a look again at another blank unit circle. If we draw a point that corresponds to an angle of 60 degrees, we know that it has a radius of 1. We also know that the distance from the origin to point A is 1. Therefore, this is an isosceles triangle. But this isosceles triangle has an angle of 60, which means that the other two angles over here also have to be 60. Therefore, I have an equilateral triangle. Now, if I bisect the line OA by dropping a line from point P straight down, I bisect that line, and because this distance is 1, I know that half that distance is exactly 1/2. Therefore, the x-coordinate of point P is 1/2. We can use Pythagorean theorem on the left-hand triangle here, where we have 1/2 squared plus k squared equals the hypotenuse squared, and the hypotenuse is 1. So I have 1/4 plus k squared equals 1. Therefore, k squared is equal to 3/4, and k is equal to the square root of 3 over 2. And again, remember, I'm only considering the positive answer because I'm in the first quadrant here. And the y-coordinate is positive in the first quadrant. Therefore, the coordinates for the point at an angle of 60 are 1/2 and the square root of 3 over 2. And again, much like we did for the multiples of 45, I can quickly come up with all of the coordinates for the multiples of the angle 30, actually. And those multiples are 30, 60, 120, 150, 200, 210, $240, 300, and 330. Notice we don't do 90, 180, 270, and 360 because we already know the coordinates of those points on the unit circle. We already know the sines and cosines of those angles. Let's look at the angle theta equals 30 on the unit circle diagram. I can draw a line that represents the point at an angle 30. And the distance of that line is 1. We also know the distance of this line right here is 1. And if I complete the triangle, this is another equilateral triangle with angles 60, 60, 60. However, the bisection is going to occur on the y-axis, so now that the y-coordinate is going to be 1/2. And we can prove using the same methods that we did for angle 60 that the x-coordinate is now going to be square root of 3 over 2. So for any angle that's a multiple of 30, that's not a multiple of 90 as well, the coordinates for those points are going to be some combination of 1/2 and the square root of 3 over 2, and their positives and negatives. Let's take a look at another picture, a diagram from your book, that lists all of those multiples of 30s. I'm not going to take the time to redraw them, but here's a diagram. Notice that all these angles, 30, 60, 120, 150, 210, 240, 300, and 330 all have coordinates that are combinations of 1/2 and the square root of 3 over 2 and their negatives. And using all silly turtles crawl, we know that in the first quadrant, they're all positive. In the second quadrant, the x-coordinates are negative and the y-coordinates are positive. In the third quadrant, the x-coordinates are actually all coordinates are negative. And in the fourth quadrant, the x-coordinates are positive and the y-coordinates are negative. The lesson here is that if you learn how to calculate the coordinates for 45 degrees and the coordinates for either 30 or 60 degrees, you can then quickly come up with the coordinates for all of the multiples of 30 and 45 without having to use a calculator. To recap, if theta is a multiple of 90, which we know is pi over 2, then the coordinates of those points are going to be combinations of 0 and plus or minus 1. And these are the 4 cardinal points of the unit circle, so to speak. If theta is a multiple of 45 and not a multiple of 90, then the coordinates are going to be a combination of plus or minus square root 2 over 2. And if theta is a multiple of 30, which we know is pi over 6, and not a multiple of 90 again, then the coordinates are going to be a combination of plus or minus 1/2 and plus or minus the square root of 3 over 2. Also, let's not forget that tangent can be found by dividing sine of theta over cosine of theta. So not only can we calculate sine and cosine based on the coordinates, the x and y coordinates, we can also calculate tangent. Let's consider an example problem where we need to find sine, cosine, and tangent for a series of angles. The first angle is pi over 3, and we know from the first part of the video that pi over 3 is equal to 60 degrees. We also know the coordinates of the point for that angle, and they are 1/2 and square root 3 over 2. Because we know the x and y coordinates, we quickly can find cosine and sine. Cosine of pi over 3 is simply 1/2. And the sine of pi over 3 is simply the square root of 3 over 2. Now to find the tangent of pi over 3, remember that we divide the sine by the cosine. In this case, sine is square root 3 over 2. And we're going to divide by the cosine, which is 1/2, but that's really the same thing as multiplying by 2 over 1. The 2's cancel out, and we're left with square root 3. The second angle is theta equals 5 pi over 6. And we know that this is, or we can quickly find that this angle is 150 degrees. Because this is a multiple of 30, I know that the coordinates for this point are going to be a combination of 1/2 square root 3 over 2 when they're positives and negatives. If we go back to the unit circle in the previous part of this video or in the textbook, we can find that the x-coordinate, or you can figure this out on your own, the x-coordinate is square root 3 over 2, negative square root 3 over 2, because we're in the second quadrant. And the y-coordinate is a positive 1/2, also because we're in the second quadrant. Again, cosine of 5 pi over 6 is simply the x-coordinate, so negative square root 3 over 2. Sine of 5 pi over 6 is the y-coordinate, so it's 1/2. Tangent is just sine divided by cosine for that particular angle. So we have 1/2 divided by negative square root 3 over 2. But again, I'm going to multiply by the reciprocal here. And you can see that I'm left with 1 over negative square root 3. If we rationalize the denominator, I have negative square root 3 over 3. The last angle, theta equals 5 pi over 4, is also 225 degrees. Notice that this is a multiple of 45. So I know that the coordinates of this point are going to be combinations of the plus or minus of square root 2 over 2. Because we're in the third quadrant, I know that they're both going to be negative. So the coordinates here are negative square root 2 over 2 and negative square root 2 over 2. I know that cosine of 5 pi over 4 is the x-coordinate and is negative square root 2 over 2. Sine of 5 pi over 4 is the y-coordinate, and it's also square root of 2 over 2. And when I go to calculate tangent, which again is sine divided by cosine, I see that I'm dividing a quantity by itself. I'm dividing negative square root 2 over 2 by itself. And of course, we're going to get 1. In the next example problem, we sort of want to do the inverse of this process. We're asked to find all angles theta such that theta is between 0 and 360, so 1 revolution of the unit circle, and cosine theta equals 1/2. Well, we know from our previous investigations that the point, or one point that has an x-coordinate of positive 1/2 on the unit circle is this guy right here. And that corresponds to an angle of 60 degrees. So let's draw a blank unit circle. And now we can label the point which corresponds to 60 degrees. Again, we know the coordinates of this point are 1/2 and square root of 3 over 2. Now cosine is positive. Keep in mind that we're only dealing with positive 1/2 here. Cosine is positive in the first and fourth quadrants. And we know that from all silly turtles crawl. So if we drop a line straight down from this first point and then draw the line or the corresponding angle, I know that this wedge right here is 60, so everything that's left over has to be 300 degrees. Therefore, that's my second and only other answer to this problem, 300 degrees. So 60 and 300 degrees both have cosines of 1/2 because they're the only ones who have coordinates with a positive 1/2 x-coordinate. And just to be thorough, the y-coordinate for 300 degrees is negative square root 3 over 2.